Well, they're ready.
Okay, good morning, everyone. We're back, day 2 of the PPIC Appendices Report, a conversation with the authors. I wanted to remind everyone who's here that lunch will be served at approximately noon. Same arrangements as yesterday, the room next door. If you're one of the first 30 people here, you can have lunch. And since there's, about that many here, I guess we'll all eat as much as we can eat. And thanks to the Watershed Science Center for providing those treats. If there are no other questions before we begin, I'll introduce Jay and we'll get on with the program. Jay?
Well, this is just a beginning with a series of introductions because I'm going to introduce the main author of this appendix, which was not me because I'm not a water treatment guy myself. I had to take those classes, but that's not what I write papers on. And we're very lucky to find Wei-Hsiang Chen, PhD student in environmental engineering at UC Davis, who specialized in water chemistry problems in the Delta, and who's done a lot of work before he came to this project on pesticides in the Delta and potential problems of pesticides for urban drinking water. So he comes to this project with a very good background in Delta chemistry, if there is such a specific field, but I guess maybe there is for us. And he, along with Christine Hounshield, did quite a lot of very good work on this, which I helped with, and we had really quite a few external reviewers. We had a lot of help from outside with people that actually run these treatment plants as well. So without further ado, I'll introduce Wei-Hsiang Chen.
Okay, thank you, Jay. So thank you for coming to the presentation for this Appendix H. So in this Appendix H, we have 3 authors, and we also would like to thank Mr. Finer for his research support. So this appendix primarily talk about the drinking water quality problem in the Delta and the associated treatment costs, and also we will have some discussion regarding the possible residual health risks posed by disinfection by product formation. So this is the outline for today's presentation. I will show you some of the data regarding the drinking water quality in the Delta for both current conditions and also the future conditions. And then we will talk about some disinfection by product that could be produced by considering the Delta water quality and also the treatment technology used in the Delta. After we having all of the information regarding disinfection by product, we can select the possible or the appropriate treatment process for disinfection and those advanced treatment technology that can provide additional disinfection by product precursor removal. Here we're not going to, in this appendix, we didn't consider all of the treatment technology because it is difficult to consider all of them. So we focus on disinfection and those technology that can help to prevent the formation of DVP. And after that, we did some cost estimation for each technology and also for different kind of treatment configuration by considering the water quality and by considering the water quality for each Delta location. At last, I will show you, I will discuss quite a bit regarding the residual health risks that posed by the disinfection by product formation, and then will be the conclusion. So at the beginning, the Delta is the largest single drinking water sources for California. So if in the future the water quality in the Delta worsen, so obviously the treatment costs required to treat the water from the Delta and also the public health risk will be increased. So in this appendix, we try to explore this kind of effect from water quality to treatment costs and the residual health risk, and by considering both current and future conditions. So before we go to the detail for this appendix, here is a table that shows some current Delta drinking water intakes. Here I have some copy for some of the table for this appendix because some of the table may not be large enough for all of the people to see. So if you need one, please take one.
And if you need to point out things on the screen, just move the mouse.
Okay, or I think I can use.
It's actually better for the webcast if you
okay.
use because the arrow will come up on it.
Okay, thank you. Currently, there are many drinking water intakes in the Delta, but here we only listed some of them, the primary one. These primary intakes for urban uses include the South Delta intakes, which include the Contra Costa Canal, and those intakes used for South Bay Aqueduct and California Aqueduct. And also the North Delta intakes include the bucket loop that feed the state water projects, North Bay Aqueduct. And if you look at the table here, you can see for those treatment plants operated by Metropolitan Water District of Southern California, they have much larger capacity as compared to the other treatment plant. So if the water quality in the Delta worsened in the future, the treatment plant operated by them could be more significantly affected. But in our appendix, it is difficult to consider all of the locations. So basically, we selected 5 of them. And these 5 locations include the 3 current Delta intakes. The first one is the Contra Costa Water District, Contra Costa Canal at Rock Slough, as shown on the figure here. And the second one is the South Delta pumps at Banks, which is shown here. And the third one is the State Water Project at North Bay Aqueduct. We also included 2 locations at upstream of the Delta. The first one is the Sacramento River at Hood. It's here. And the third one, the fifth one is the San Joaquin River at Vernalis. Even though currently there is no plan to use drinking water, to use Sacramento River as a drinking water source, but we think by including this location, that can help us to compare the water quality at different Delta locations, and also to understand this Delta inflow. So after selecting those Delta locations, we chose some drinking water constituent of interest in this appendix. Because the primary objective of this appendix is to investigate the effect of water quality to treatment costs and health risks when you have, for example, like sea level rise in the future. So the salinity is the major concern in this appendix, and that includes 3 constituents, the electrical conductivity, bromide, and chloride. And we also have data regarding total organic carbon and dissolved organic carbon. The reason we included them is because they are the primary disinfection byproduct precursor. And we also have some data for nutrient. We represented those concentrations as total nitrogen and total phosphorus. And the last constituent we consider in this appendix is pesticide and herbicide. So even though some people may argue that pesticide and herbicide may not be as important as compared to the other constituent, but we believe this constituent can pose risks to the environment and the public health. And more importantly, in recent years, some study has found that some pesticide or herbicide can actually be a potential precursor for disinfection byproduct. So therefore, we also included some data regarding the concentration of pesticide and herbicide in the Delta. So here I will show you some of the data regarding the current water quality in the Delta. The figures show the bromide concentration at each Delta location we selected in this appendix. The reason I show bromide is because we found very similar seasonal pattern for EC, bromide, and chloride. And also, it is because bromide is actually more of concern for disinfection byproduct, because bromide basically can react with different kind of disinfectant to form bromide or other kind of brominated disinfection byproduct. If you look at the data here for the locations of South Delta pumps, for those South Delta pumps and San Joaquin River and Contra Costa Canal intake, they have much higher bromide concentration. And And currently, CalFAT has a record of decision for bromide target concentration of 50 microgram per liter. So if you look at those concentrations, they have been exceeded. They have exceeded this target concentration, so indicating that bromide could be a concern for this location. And for Sacramento River, you can see a much better water quality with respect to bromide concentration at this location. So basically, in our result, we found salinity is a problem, particularly for the location of South Delta and San Joaquin River. And for TOC and DOC, as I just mentioned, they have potential to react with chlorine and ozone to form disinfection byproduct. So basically, in your source water, if you have high level of organic carbon, that means you require more disinfectant to reach your disinfection goal. In our result, for the location of North Bay Aqueduct, this location has a relatively higher TOC and DOC concentration, and also with a very obvious seasonal pattern. You can see the peak starts from January and to the early summer or the end of spring. But overall, the data of TOC and DOC usually have less seasonal variability than as compared to the concentration of salinity. So for nutrient are represented as total nitrogen and total phosphorus concentration. And we found that San Joaquin River has the highest nutrient concentration, and it does make sense because we have a lot of agricultural activity in San Joaquin Valley, so that can contribute the loading of a nutrient to this location. And for pesticide and herbicide, we collected data from the database of DWR, Department of Water Resources, and DPR, Department of Pesticide Regulations. We found at 4 locations, North Bay Aqueduct, South Delta Pumps, and Sacramento and San Joaquin River, they do have some pesticide and herbicide detection at this location. Therefore, even though San Joaquin River has a better water quality with respect to bromide and TOC-DOC concentration, it does have some pesticide and herbicide contamination. So after knowing the current drinking water quality, we would like to know the future water quality for these selected delta locations. So basically, the way we did in this appendix is we use a hydrodynamic modeling from Appendix C. So that hydrodynamic modeling gives us a result with respect to EC concentration for this location. And this modeling considers 3 different long-term conditions, 1 and 3 feet of sea level rise, and the failure of Delta's western island. And after that, we use a regression model developed by Metropolitan Water District of Southern California, which is a salinity correlation analysis particularly developed for Delta location. So it is okay to use that regression model, and we use the model and use the data from the hydrodynamic modeling to estimate the bromide and chloride concentration at those selected Delta location. But here we have 2 important assumptions. The first one is we assume that Contra Costa Water District only use the water intakes at Rock's Roof. But practically, they have 3 drinking water intakes, and they have the 4th one under construction. So basically, this may not be exactly perfect for in reality, but this can help us to simplify this prediction model. And also, because it is kind of difficult if you consider all of the conditions, because in reality, Contra Costa Water District will select the drinking water intakes with better water quality when the water quality in the delta worsen. So there is no specific rule to say they will use which intake. So in our model, we just assume they use this drinking water intake from Rock's Roof. And this water intake typically has the worst water quality among those water intakes they use. And the second assumption is we assume that no change in upstream or in delta operation will be operated to meet water quality when sea level rise or delta's western island fail. So basically, these 2 assumptions is prepared to help us to do this prediction model more easily. And also, in another way, you can think by using these 2 assumptions, we can understand how bad water quality could be in the future when sea level rise or the delta's western island fails. So here is the table that quickly summarized the water quality the current and future water quality in delta locations. For the Sacramento River and San Joaquin River locations, we didn't do prediction for these two locations because we assumed that when sea level rise, the water quality at these two locations would not be significantly affected. So we only have the current water quality data for these two locations. And for Nose Bay Aqueduct, because when we prepared this appendix, the hydrodynamic modeling result was not yet suitable for this location, so we didn't include the data for the Nose Bay Aqueduct. But if you look at the data for South Delta pumps at Banks and the Contra Costa Water District, you can see when sea level rise to 3 feet, the bromide concentration can as high as 0.84 milligram per liter for the location of Contra Costa Water District, which is much higher than the CALFAT record of decision target concentration for bromide. And as I just mentioned, for TOC and DOC, the Nose Bay Aqueduct has a relatively higher concentration as compared to the other locations. So by having those water quality data, we selected some disinfection byproduct. The way we selected disinfection byproduct is we consider two primary water quality constituents, TOC and bromide. The reason we chose bromide is because, just as I mentioned, salinity is important, so we selected bromide. And TOC is the major concern because it is difficult for us to consider all of the constituents. So we choose these two as the primary constituent, and based on these two constituents, we can select disinfection byproduct and select the appropriate treatment technology. However, currently there are more than hundreds of disinfection byproducts that could be formed from different kind of disinfectant and different kind of water quality constituent. But in our appendix, we have disinfection byproduct that include halomethane, haloacid, and total organic halide. They are the disinfection byproduct mostly regulated and studied. And we also included aldehyde, bromide, and halonitromethane. We chose this because they can be formed by using ozonation and UV irradiation. So I will talk about this technology in the later slide. And also because we concerned about bromide. So we also selected bromide and some brominated disinfection byproduct. So for treatment process, as I mentioned in the beginning, we only focus on disinfection and those advanced treatment technology that can provide additional disinfection byproduct precursor removal. And these constituents include TOC and bromide. So we selected this treatment process, and that includes two alternative disinfection, ozonation, which has been widely used in the water treatment plant that use delta water, and the other one is UV irradiation. And for the other treatment technology, we have enhanced coagulation that can remove TOC, and also adsorption, membrane filtration, and we also have some discussion regarding magnetic ion exchange. Even though this is not a common technology currently in delta, but because it has the ability to remove both natural organic matter and bromide, which are the two primary constituents we concern in this appendix. That's why we included particularly this technology in this appendix. But before we go to the detail for those technology, here is a quick table that shows the current treatment process used in the treatment plant that use delta water. As you can see, for disinfection, many water treatment plants that use delta water already have ozonation in their treatment plant. The only difference is how they use this technology. And they also have chlorine and chlorination for their treatment plant because when you use ozonation, you require chlorination or chlorination to provide sufficient disinfectant residue in your treated water in the distribution system. For adsorption, it is also common in the delta. The only difference is the media they use for this process. And for membrane filtration, it is not so common, only used in some of the plants in the delta. So then next we did some cost estimation for each technology. And these costs were developed in terms of capital and operational and maintenance costs. And they are developed as a function of source water quality constituent, primarily TOC and bromide. And we consider the system size that range from 1 to 520 million gallon per day, so which basically almost cover all of the system size of treatment plant that use delta water. And in the result, we found that UV irradiation is relatively cost effective as compared to ozonation. But it is important to know that this technology requires a lot of energy costs, for example, like electricity and lamp cleaning. So that means the cost may be even higher, especially for the operation and maintenance costs. And for the other technology, our results shows that the lowest costs are GAC, and followed by microfiltration, ultrafiltration, and the nanofiltration has the highest cost. But before we use those cost information to estimate the treatment cost for each delta locations, we need to know the limit of technology so that we can estimate the best combination of treatment technology with minimum cost, but also ensure the health risks provided by drinking water. So the way we did is basically we collect a lot of information from published study and information from local and state and local agencies. And in the table here, that shows our result. So basically, we assume ozonation as the base treatment technology. And when you have higher TOC concentration, you may need to add GAC or enhanced coagulation to remove those high TOC concentration. However, when you have high bromide concentration, then you may need to add magnetic ion exchange and ultrafiltration, or just replace your ozonation to UV to prevent the formation of those brominated disinfection byproduct. But because we use a lot of information from different agencies, so the result could be slightly different because of many site-specific conditions and different safety factors operated by different water treatment plants at different locations. But here is the best estimation we have in this appendix. So after that, we use all of the information, including water quality in every location and treatment costs for different treatment technology, and also the technology limit. We estimate the treatment cost will be required for each delta locations. In the table here, so basically we have location that includes Sacramento River. Even though currently there is no drinking water treatment plant that use Sacramento River, but the water quality at this location represent the water quality that will be available for water agencies if a peripheral canal was established to replace the South Delta drinking water intakes. And we also have the cost estimation for North Bay Aqueduct, Contra Costa Water District, and the treatment plant that use the water from the South Delta. If you look at the treatment costs for different locations, as you can see, for those locations with higher bromide concentration, for example, like Contra Costa Water District, the ozonation cost was much higher than the cost required for those locations with better water quality with respect to bromide concentration. And the result that shows eventually that UV disinfection combined with other treatment could be more cost competitive as compared to ozonation combined with other treatment technologies. But for the future water quality conditions, the table here shows our estimation result. As I just mentioned, the Sacramento River, we assume that water quality at this location will not be significantly affected. So we only have one treatment cost for these locations. And because we didn't have the future water quality data for North Bay Aqueduct, so we didn't include their cost estimation in this table. And for the cost highlighted in bold, the sky blue color here, they represent the most likely treatment process cost for each location and for different conditions here. So if we, for example, like Contra Costa Water District, under current condition, you have a bromide concentration 0.25 milligram per liter. So this enhanced calculation combined with ozone may already enough for you to treat your source water. But when you have 1 feet sea level rise, you have higher bromide concentration, so you may need to add GAC to help you control your treated water quality. Even though GAC is not designed to remove bromide, but basically when you have high bromide, you also need TOC to react with disinfectant to form disinfection byproduct. So if you are able to remove your TOC to an even lower level, that can also be a strategy to help you to control the formation of disinfection byproduct. And also that can give you a lower treatment cost. That's why for this condition, 1 feet sea level rise, we suggested this treatment technology of enhanced coagulation and ozone and GAC. But when you have 3 feet sea level rise, the bromide concentration is as high as 0.84 milligram per liter. In that case, this kind of strategy would not be able to help you to control your treated water quality. In that case, you will need to add magnetic ion exchange that can remove bromide to control your drinking water quality. But that also significantly increased the cost required for these locations. And for those costs highlighted in the red color, in the pink color, that represent the cost may not be practical for this by using this kind of treatment configuration. So for example, like 3 feet sea level rise at Contra Costa Water District, if you only use enhanced coagulation versus ozone, even though it can give you a very low treatment cost, but you may have a significant formation of disinfection byproduct or some contamination being present in your treated water. So for the residual health risks, in our appendix we consider two disinfection technology. The first one is ozonation, and the advantage of using ozonation is it can avoid the formation of those commonly regulated disinfection byproduct, but it also produces its own disinfection byproduct. And of those ozonation disinfection byproduct, bromide is more of concern as compared to the other byproduct. And for UV radiation, since it is a physical reaction as compared to the common chemical disinfection process, it has fewer disinfection byproduct issues. But when your source water has high turbidity or a high suspended solid concentration, this technology could be ineffective. And also, recently some studies have found that for some specific disinfection byproduct, their formation could be enhanced by using UV irradiation. But I think the most important concern by using these two technologies here is basically ozonation and UV. They don't provide a disinfectant residue in your treated water. So that means you require additional chlorination or chlorination to provide a disinfectant residue. So in that case, if your treatment plant cannot remove bromide in your source water, it is possible that at the point of chlorination or chlorination, you may have a high bromide to TOC ratio because you are only able to remove those TOC. In that case, more brominated disinfection byproduct can be formed, and this brominated disinfection byproduct has been known as more potent and more toxic as compared to those known chlorine-containing counterparts. So here are some of the conclusions from our appendix. In our result, we found that salinity is more serious at the South Delta intakes and San Joaquin River. And for North Bay Aqueduct, it has a relatively high TOC and DOC concentration. And even though Sacramento River has a better water quality with respect to bromide and TOC concentration, but it does have some pesticide and herbicide contamination. And even though UV irradiation is more cost effective, but it is likely that ozone will continue to be used as a primary disinfectant for agencies that use delta water as their primary water sources. Here is a table that quickly summarizes the treatment cost result we have from our appendix. So we have 4 different conditions: the current 1 and 3 feet sea level rise and the failure of Western Island. And for Sacramento River, we have 2 different system sizes, and we assume the water quality will not be significantly affected by the sea level rise, so we have the constant treatment cost under different conditions. And for Contra Costa Water District and those treatment plants that use South Delta water, we have different treatment costs for different conditions, and that consider the most appropriate treatment combination for each water quality conditions. And we found that Contra Costa Canal intake would have the highest treatment cost increase as compared to the current condition and those future water quality conditions. And this cost difference between the South Delta and Sacramento River could increase from $20 to $60 per acre foot to $100 to $500 per acre foot. So if you assume 1.5 million acre foot of delta water used per year, so this treatment cost difference could increase from 30 to 90 million per year currently to 200 to 1,000 million per year in the future. So this cost difference could be very significant. And in addition to the concern regarding the treatment cost difference, the residual health risk can also affect the strategy of manage the delta water sources. However, in addition to modify or changing your current operational strategies, such as adding the new treatment technology, other strategy, for example, like blending or using other source waters with better water quality, even though this may further change your treatment cost, but it could significantly help you to control the quality of your drinking water. So at last, we would like to thank to many people who help us to understand the drinking water quality problem in the Delta. We have a lot of help from the people from different state and local agencies. So without their help, I think it is very difficult for us to prepare this report. So we would like to thank them for their help. So at last, I would like to thank you for coming to this talk, and any question or comment will be very welcome. So thank you very much again.
Open for questions, discussions. We've got 20 minutes or so.
Well, I have one. We did our final assessment report for the CalFed, our drinking water quality program. The peer reviewers pointed out that we hadn't considered organic nitrogen as a possible precursor for formation of nitrosamines. Is that something that you looked at and considered?
I think that's one of the reasons that we include pesticide and herbicide and those nutrients in our appendix, even though we didn't further consider the disinfection byproduct that could be formed from this precursor. But I think nitrosamine is of concern in recent years, actually. So if you want to more detailedly to consider the formation of disinfection byproduct, I think those constituents, including pesticide, herbicide, and organic nitrogen, would definitely be important. And because I also work for another project in UC Davis, and which is a project basically that studied the formation of NDMA, nitrogen nitrosamine, from one specific herbicide, diaram. And in our study, we also found some formation of NDMA from this herbicide. So basically, that also support this question. So basically, some of the pesticide and herbicide and organic nitrogen can also be a significant precursor for disinfection byproduct. But in our appendix, because of the time strain, and also we would like to focus on the effect of sea level rise, so we only focus on TOC and bromide. And also we assume that those for example, like pesticide and herbicide and organic nitrogen, could be removed by those technology before disinfection. So that's why we didn't look at them in this appendix. But I think definitely those constitute like pesticide and herbicide and organic nitrogen would be important if you want to detailedly look at the disinfection byproduct problem.
So I mean, the importance is that it kind of affects your decision about how much better Sacramento River water is than the rest of the Delta, because Sacramento River water does have significant amounts of those herbicides and organic nitrogen. We're pretty sure. We haven't looked at it in very detail. So, and what technologies are effective for organic nitrogen and the herbicides? Which ones did you?
Typically, the technology used to treat those constituents, to the best of my knowledge, would be absorption. So the absorption technology would be, if I remember correctly, it would be effective to remove those organic nitrogen and pesticide and herbicide. So I think that would be one strategy if you need to use a location that has a water quality problem like Sacramento River, which has maybe some detection of pesticide, herbicide, and organic nitrogen.
Okay, so your technologies that include GAC would be appropriate.
That's right. That's right.
Okay.
I had a question. I think I must have missed something. And forgive me because the specialized aspects of the treatment technology are not my area. You implied it towards the end of the presentation that the technology for treating bromide was in some way dependent upon the levels of TOC. Am I right?
It's not. Okay, let me explain that
Yeah,
again.
please,
Okay.
because then you don't have predictions of TOC, and so I'm trying to work out how you then did the
Okay, that's
predictions
right.
for the cost of bromide if it is dependent on
Yeah,
TOC.
so I didn't mention that in this presentation. We did have some prediction for bromide concentration for each location.
Yeah, for bromide, yes. But
That's
for
right,
TOC
but
not.
for TOC, we didn't do prediction for TOC concentration. There are a few assumptions for this appendix. The first one is we assume that TOC level will not be significantly affected by those future water quality conditions. For example, when you have sea level rise or the failure of Delta's Western Island. But of course, this is an assumption. And also the other reason is our hydrodynamic modeling cannot use to predict the concentration of TOC. So that's why we determined that we use the TOC concentration from the current water quality, and we assume there will not be a significant difference between this current and future condition. And we use that TOC concentration and bromide concentration predicted to estimate the treatment cost. But just as you mentioned in the question, if you have high TOC or high bromide, you may need to use some specific technology, for example, like magnetic ion exchange to remove bromide. But it doesn't depend on the concentration of TOC. But
It doesn't depend on the. Okay.
yes, and
I'm sorry. I want to get the negatives right here. Does treating bromide depend on the concentration of TOC?
my answer would be no.
Okay.
Okay.
Got it.
And the reason we use treating TOC to handle those water quality with high bromide concentration is because if you have a high bromide concentration, if you just add magnetic ion exchange in your treatment plan, that will significantly increase your treatment cost.
Absolutely.
But if you use GAC instead of magnetic ion exchange, even though that remove TOC, not bromide, but you further reduce your TOC level. And because the bromide need to react with TOC and disinfectant to be disinfection byproduct. So if you remove TOC, even though you have high bromide, you can also control the formation of disinfection byproduct. That's why we have this kind of estimation in this appendix. But I have to mention that this kind of strategy also poses another risk, as I mentioned in the end of this presentation. So you will have high bromide to TOC ratio when you have additional chlorination or chromination. And that can be another disinfection byproduct formation issue.
Thank you.
One last question. I don't want to add to the list of disinfection byproduct issues, but did you look at iodide at all? Do you have any information about iodide in the Delta?
No. So for this appendix, we didn't look at that. But for some of the disinfection, for not just some, many disinfection byproduct formation study, that is an important constituent in addition to bromide when you have high salinity. We have
An emerging issue in the Delta is the increasing propensity to have toxic algal blooms, particularly microcystis that produces soluble organic toxins. What implications might the production of this material, particularly in large quantities near the pumping stations down south, have on treatment costs downstream?
Can you say again your question?
Microcystis, a cyanobacteria, is blooming in prolific quantities now during the warmer summer months in the Delta, and much of it is down near where the pumps are in the south part of the Delta. I was curious as to what implications that might have on treatment costs and whether these various treatment pathways that you've discussed are effective in removing these kinds of toxins from the water supply.
For those constituents, to be honest to you, I'm not familiar with that kind. I don't really know the answer for this question. But I will assume the typical treatment process prior to disinfection may be able to treat some of those constituents in the source water. So when you, for example, in this appendix, when you only look at disinfection, those may not be a major concern as compared to like bromide or TOC. Because in this appendix, we didn't look at the treatment technology before the disinfection. So I have to say I'm not really familiar with the answer of this question.
I think that's generally true. I think the problem with the microcystin is usually if you lyse the cells and you release the toxin from inside the cells, that's a problem. And you don't normally do that in drinking water treatment. You're going to get the algae out before you hit it with your disinfectant in most cases. Or you might have to adjust your treatment in some cases if you had enough of it. But I think that's generally the case.
In some of our conversations that we had leading up to this appendix with some of the local water agencies, some of them mentioned some concerns with algae in the treatment processes.
Yeah, I think
It's an issue in Australia. I mean, a lot of the reservoirs have big microcystis blooms, and they do have to be careful when, how and what they treat during certain times, particularly during the senescence period, when the blooms are starting to die off.
I had a more general question. I think it's back fairly early on in your presentation, and I just wanted to make sure I got the information right because I think it helps set up the whole coming issue, if I would, or if you will, bear with me. You mentioned there was you displayed a current water quality slide, and it had the now famous water wheel diagrams, and it showed, I think, bromide concentrations that were at or near exceedance for local water quality regulations. I got the impression that was currently. Did I understand that slide correctly in that I took away from that we're right up against our regulations now, and that with sea level rise, we are to expect large-scale and persistent exceedances of bromide concentrations at those locations? Is that right?
Yes. So if you look at the current water quality data with respect to bromide concentration, the concentration actually for the South Delta has exceeded the current standard. For example, like the CalFed record of decision target concentration.
Well, I don't know if that's a record. That's not a standard.
That's a target.
That's a target.
That's right.
There's sort of a very important legal difference.
Right.
Yeah, so it is an important difference.
It's MDL, it's a rod target.
It's a rod
It's
target.
not a 1641 criteria.
Okay, that's right. When I hear that we're in exceedance now,
My understanding is that there is no standard for bromide.
There's no standard for bromide. There are standards though for TDS, so for EC and TDS. There's a secondary MCL for that. It's a kind of progressive standard. It starts at you're looking at EC there, so the standard starts at about 900 and goes up to like 2,200, and depending on what level you're at, you're supposed to take different actions, look for alternative water sources, and then you get up to 2,200, and you can't serve water with that much salt in it.
So it's fair to say that we're at the sort of tolerable limit of our desirable water quality now, and it's not likely to do anything but get worse. Is that true?
I would say that the water quality we're at now presents treatment challenges. People have to use a pretty creative balance of treatment technologies to meet the standards.
Because
And I guess I have to say one thing that impressed us when we worked on this appendix is just like we saw when we worked on Appendix B on the local delta levees, that the local levee engineers were really getting quite creative about making things work. In our conversations with the local treatment people, they'd been really quite creative about trying to make this work. Certainly it cost them some more, certainly it was inconvenient, but they've been able to come up with some workarounds that probably 10 years ago they didn't expect. Maybe Paul would probably have a better feel for this.
Jay, I don't think I was going to address your comment. I didn't disagree with it. But I think if you really step back from what all these numbers are saying, rather than looking at the numbers, the conclusion I come up with is if we have one of these high sea level rise scenarios or the island failures, these aren't water qualities that drinking water agencies would want to try to treat their way around. Because we're assuming that we know. I think you discussed a lot. There's a lot of uncertainty, but we only know about certain disinfection byproducts now. But that would have to be taken into account in the future. What other disinfection byproducts would we have in a water quality that's that poor?
And I think that raises another issue that we sort of mentioned, I think, in the report, but we don't talk about a lot because it's a little bit speculative, but I think not terribly speculative, in that just as we're likely to see worse water quality here from a treatability perspective, we're also likely to see we're not likely to see less regulation of disinfection byproducts. We're likely to see probably more regulation of disinfection byproducts in this time frame. And that would make even, we're able to get by with the current water quality okay, but we might see additional costs from tightening of drinking water standards as well as from worsening raw water quality. So in some ways, I think our cost estimates might be low from this perspective, just as they might be high if the creativity continues to be up to the challenge.
Do the cost estimates include the capital cost for the Sacramento? Yeah, okay.
Are there arsenate exceedances in any of these water supplies?
excuse me?
Are there arsenate exceedances in any of these water supplies?
No.
The only arsenic problems I'm aware of come from groundwater in the
Groundwater in a lot
southern
of
Central
places.
Valley.
Yeah, arsenic in the delta is pretty low, a couple parts per billion. But when you get down into one of the issues is when you start talking about doing conjunctive use and pumping in water and using groundwater banks, you really have to look at the arsenic issue because it is a pretty potent carcinogen too, and the standards are low, but the residual health risk issue is an important consideration there.
Yeah, so Metropolitan deals with that problem with some of our pump-in programs in the Central Valley. So some of our the groundwater pump-ins are actually treated prior to being put into the aqueduct.
That's the good news about arsenic. It's fairly easy to treat.
Yep. Yeah.
Okay. Any other question?
Additional question?
I just want to make sure that I understood, I guess, what Paul was saying, but what it sounded like is whether it's 1 foot sea level rise or more, or the Western Island failures for the water districts, it just wouldn't be economical, it wouldn't make sense to use that as a water supply. Is
It
that
all
what you were
depends on your
saying?
choices, I think. If that's the only water supply you have,
Yeah.
it will cost you more.
Economics will change, perhaps.
What we try to do is quantify the cost.
Yeah.
And there's our estimates of the numbers.
And just to add, there's another cost option, which is to release more flows from the
That's true too.
reservoirs and have kind of manage the salinity that way.
So you might choose to have more delta outflow to push the salts back. So someone's going to pay either in terms of quality, treatment costs, or quantity, or maybe all of those.
So is there any other question? Okay. Okay, thank you very much.